Water. It's the ultimate life support system.
Water is the essence of life.
It's so basic, but it's a flood of contradictions.
Water is really hard.
And it's stronger than a speeding bullet.
Bulletproof glass will stop a 50 caliber shell, yet we can erode it with a water jet.
We just can't seem to get enough of it.
They would use 2,000 gallons of water in every 30 miles.
Now, water on how stuff works. Silvery, intangible, just plain wet. Water is all around us, yet it remains a mystery. While water makes up around 55% of our bodies, why will just a small amount cause a person to drown? Why are rivers fresh, but oceans salty? Why does solid ice float on liquid water? And can you really grow water from a seed? It's all part of how water works. Water is strange. It takes an unbelievable amount of water to grow a single apple, and almost 50 times more for a pound of beef. And there's 6 times more water in the sky over our heads than in the rivers under our feet. We all think we know water, but our understanding is, well, muddy at best. Water. It dices, it slices, it steams, spins, and sprays. But for every plant or animal on the planet, the essence of water remains this, keeping us alive. A steel fender built for a custom motorcycle, and a ballistic-grade material designed for bulletproof, blast-proof armor. They're among the strongest engineering materials around. But today, they'll both be cut down to size by one of the world's most powerful forces. Forget about bubble baths and designer bottled water. This is the Seattle Research Lab of Flow International, the world's leader in ultra-high pressure, or UHP, water jet cutting. So why is water a cut above a welding torch or diamond-edged saw blade? It all begins simply enough. A hydraulic pump takes in regular tap water and pressurizes it. For water, increased pressure through a small aperture equals increased velocity. And since, as we all remember from school, force equals mass times acceleration, increased velocity means serious sliceability.
You can take a very small fraction of Niagara Falls and concentrate it in a very small beam, and that will be able to cut very hard material. Just like laser will focus the light to make a laser beam.
The water is forced through this tiny opening, which is ringed with a gemstone so it won't be cut to shreds by the water jet. Just like constricting a garden hose with your thumb concentrates a stream of water out of the nozzle, concentrating a volume of water through a tiny opening produces this. At the business end of the jet, the water is traveling faster than any jet plane at Mach 4, 4 times the speed of sound, at a pressure of 87,000 pounds per square inch.
So at that point, it's really one of the most powerful water jets on Earth.
How does water, the same soothing liquid we drink and bathe in, cut through materials we use to build skyscrapers? The answer is one of water's grittiest abilities, erosion, the removal of solid material by the force of moving wind or water. Water starts eroding material the second that it hits Earth.
Erosional processes begin with raindrops impacting the land surface. And as a raindrop hits the ground, it exerts quite a bit of force on those particles and can actually detach them and move them. Erosion also occurs in a river like the one that we're floating on here.
Well, water is a very powerful force, certainly powerful enough to carve away at rocks. As it travels downstream, it carries along with it all the little tiny particles of sediment that it picks up along the way, scouring the sides and the bottom just with the force of its movement.
The evidence of this 1-2 punch, water and moving sediment, is everywhere. Like these grand canyons carved out by the Colorado River. Some are a mile deep, the result of tens of millions of years of erosion. Back at the shop, high-pressure water alone can slice materials as hard as glass. But throw in a little fine sand, and it can cut through pretty much anything.
By adding abrasive to the water, you're increasing the strength of that water over 100 times.
An abrasive high-speed water jet even chews through incredibly hard ballistic ceramic and glass used in the most advanced blast-resistant armor.
It's the unique characteristics of water and how erosion works. Bulletproof glass will stop a 50 caliber shell at 200 feet, but yet we can erode it with a water jet just like we would a standard piece of plate glass in your house windows.
The water will also drill right through to the steel guide under the material. In fact, the only way to stop the water is with more water. A 4-foot deep trough of water helps absorb the 2,400 mile-per-hour jet before it bores a hole in the floor. What's the upside to using water as a cutting tool? Just about everything. Water's inexpensive and reusable. It makes a very precise cut. And since it does its job without heat or friction, the cutting edge doesn't distort the material, and it never gets dull. Water is anything but dull. Water's physical properties, tough yet fluid, make it the backbone of everything from tiny cells to the world's weather systems. It's a small, simple molecule that covers 70% of the planet. It's a liquid that carves out the planet's surface, and an electrically lopsided chemical that makes all life possible. And over time, it cuts like a knife. But what makes it so tough? As in much of life, the key to success is sticking together. Water's countless molecules flow as if one, and that flow has everything to do with water's electrochemical makeup.
Water is something called a dipole. A dipole simply means that it's a material that has one kind of charge on one end and another kind of charge, the opposite one, on the other end. So it's got a slightly negative part over near the big fat oxygen atom, and near the hydrogen atoms, it's a slightly positive part. So this enables water to do something pretty spectacular. When it's in combination with other water molecules, the hydrogen parts get attracted to the oxygen part of its nearest neighbor, and so the molecules kind of squeeze together.
This attraction, known as the hydrogen bond, is at the core of water's amazing properties. It makes water tough enough to provide the stiff but fluid structure of plants and animals. H2O's molecular structure also allows for a truly miraculous transformation. As water freezes into a solid, the hydrogen bonds form a crystal lattice that has a lot of empty space in it. Unlike nearly every other substance known to man, it becomes less dense as a solid than a liquid, turning traditional physics on its head. The result? Ice floats on water.
Because of this, when we freeze a body of water, it freezes from the top down, not the bottom up.
If ice didn't float, if water became more dense as it froze, then our ponds, our lakes, our oceans, rivers would freeze from the bottom up and would eventually be solid ice and would be much less conducive to life.
The hydrogen bond enables life as we know it, but because of this bond, it takes considerable heat, depending on volume, whether supplied by a stove or the sun itself, to raise water's temperature even 1 degree. This ability to absorb heat is known as heat capacity.
Water actually has the second highest heat capacity of all of our common substances on the surface of the Earth, with ammonia actually is the only common substance that has higher heat capacity.
That's why we use water in cooling our internal combustion engines, our power plants, and the human body. The evaporation and perspiration keeps our temperature regulated. And similarly, one of the reasons that our change of seasons is gradual rather than abrupt is that water absorbs heat and releases it rather slowly. So the water on the planet tempers the change of seasons.
The deep blue oceans suck up solar energy, much like the roof of a dark-colored car on a sunny day, acting as a planet-wide heat engine that circulates water currents, air currents, and precipitation. The sun causes water to evaporate from dewdrops, streams, ponds, oceans, and lakes. The vaporized water rises, cools, forms clouds, and eventually condenses into rain droplets or snowflakes. It all comes back down to Earth, And one way or another, whether it percolates into the groundwater or flows on the surface of lakes or streams, virtually all water eventually works its way back to the ocean.
So what happens is in the cycle is it's repeated. All water on Earth has been recycled millions and millions of times.
Later, falling water. It gives us the rush of whitewater rapids and much of the world's electricity. But how? Next, can you name a solar-powered water pump that can also grow leaves? You probably have figured out that water equals life. To begin with, it is the perfect medium in which life can form and reform. But why? What properties of water make it the fluid of life?
Water has a very important role in all of the chemistry that happens. A huge array of materials will dissolve in water. And because water enables other things to dissolve in it, it provides a medium where those things can recombine and form new chemicals.
Water takes a kind of divide and conquer approach to breaking down other chemicals. In the case of table salt or sodium chloride, water's negatively charged oxygen atoms surround the positive sodium ions, while the positive hydrogen atoms surround the negative chlorine ions. By splitting the two elements apart, water literally breaks down the structure of the salt.
Moreover, because water remains liquid at the conditions of the surface of the Earth, you can move around in all different kinds of directions. That's called degrees of freedom. So things can move around, flip around, vibrate, stretch, rotate, and then they're able to try novel combinations and hook up in new ways.
This surely helped life get started on the early Earth. The chemicals, the raw ingredients that make up life were constantly sloshing around, bumping into each other, and combining into new chemistry. Over millions of years, that process can lead to living organisms. But to really see water's life-giving function, we need to check in with the plant kingdom.
In a plant, an important function of water is structural. The plant cell is like a water balloon. It maintains its shape because of the pressure of water inside the cell pushing out on the rigid cellulosic wall.
Water also has an almost magical ability as a chemical reactant. In other words, water encourages chemical reactions that change the nature of other things. For instance, the chemical transformation that water makes possible within plants.
So plants make their own food using light. It's called photosynthesis. And when they do photosynthesis, they take the hydrogen away from the oxygen in water, and they use the hydrogen with the carbon dioxide in the air to make sugar. It's alchemy.
Luckily for us animals, the chemical reaction also produces oxygen as a waste product.
It's a totally wonderful relationship between plants and animals enabled by water.
But plants and water have another dramatic impact on our atmosphere. Using a remarkable system, plants transport water from their roots to their leaves, where photosynthesis takes place. Water, with its high surface tension, the elastic quality of a liquid surface that makes it hard to break, is able to travel up the vascular system of even the tallest trees. Once at the top, it evaporates back into the air through the leaves or needles. A single redwood releases up to 500 gallons of the precious liquid through its needles in one day. So how does it get up there? A solar-powered hydraulic pump.
Water molecules, they attract each other. And for each water molecule that leaves the liquid column in the leaf, another molecule will move up. And the net result is that by evaporating off the surface of the leaf, we have a whole stream of water moving continually from the soil into the root and eventually out in the leaf.
This silent, invisible, molecule-by-molecule movement of water upwards through a plant represents the single biggest use of water by human beings. As a commodity, nothing in water's portfolio compares to irrigation, especially in the western United States.
If we look at water use in, for instance, the state of California, or Utah, or Arizona, the vast majority of water which is used for human purposes is used in irrigation. In the state of California, maybe 80% of our water use, maybe even more, is utilized for irrigation for growing crops.
In other words, the vast majority of our water becomes food. But it doesn't come easily. To grow even a single apple requires 25 gallons of water.
And for every pound of meat, it takes about 1,200 gallons of water. And in the United States, because we have a relatively high meat content in our diet, every day we use about 1,600 gallons of water for every human just to produce the food that we eat.
California, which grows the majority of the nation's fresh produce, is blessed with fertile soil and a year-round growing season. But the Golden State and its neighbors from Nevada to Colorado don't have a lot of water. Or more accurately, the water tends to fall up here, in mountains up to 14,000 feet tall. The rest of the region, with few exceptions, ranges from semi-arid to bone dry. The Western state's bold solution to this unequal distribution of water has been to dam the region's precious few rivers, including the Colorado, and divert them thousands of miles to lands that get as little as 7 inches of rain a year.
When you look at the scale of water management worldwide or over history, you can look at ancient Rome and the aqueducts, but these things pale compared to the water projects in Western North America.
The crown jewel in this system is Hoover Dam. Although completed over 70 years ago, Hoover Dam remains one of the most staggering achievements ever. It did the unthinkable, taming the wild Colorado River into giant Lake Mead, the largest man-made reservoir in America.
To hold back the tremendous forces and pressure of the water in Lake Mead, Hoover Dam is like a small mountain here in this canyon. It's 660 feet thick from front to back, upstream to downstream. So it's just huge, hundreds of feet of concrete, and it's just massive, and over 700 feet tall.
It has to withstand, at the base, a water pressure of about 45,000 pounds per square foot, because behind it is Lake Mead, which stretches for about 110 miles and holds something like 28 million acre-feet of water when at capacity. So you can imagine this is not only a huge engineering feat in terms of its size, but the stresses that it is designed to bear are quite incredible.
The dam was built primarily to bring water from the Colorado River to the dry farms and cities of California, Nevada, and Arizona. Today, water from the Colorado River supplies at least 25% of the nation's fresh produce.
Depending on the time of year, maybe as much as 50%. That is a huge portion of our food supply in this country as a result of the Colorado River that is now controlled by Hoover Dam.
Water will make the desert bloom, as long as you're willing to move it. Later, can water turn gravity into electricity? Next, a lazy trip down the river? Not when you're falling over 3 miles. Colorado River shimmers in the summer sun. It's a jewel with many facets because the river's waters are unpredictable.
Despite the fact that I row down this river essentially on a daily basis, I really never tire of the beauty of this place. You don't find this in a cubicle.
But just around the corner, water can turn from friend to deadly foe. A smooth flowing current becomes chaotic rapids.
I can't really think of a force that I encounter on a daily basis that even comes close to the power of this river. You turn your back once, you mess up in a small way, and turn into a pretty big problem pretty fast.
What physical forces cause water to suddenly kick it into high gear?
White water is formed usually by a combination of 3 different forces or actions within the water itself. The first is a gradient drop. If the gradient is going down quickly, you can have some very, very swift water. Secondarily, we've got constriction. Different rock layers can create tighter channels. Going around a steep bend in the river can constrict the channel. And then the third thing is obstructions. Rocks falling off the cliff wall, rocks being swept into the river by flash floods.
The steeper the gradient, the greater the change in velocity. The Colorado River makes one of the steepest drops of any major river in the United States, falling 13,000 feet in elevation between the Rocky Mountains and the Gulf of California. Two other factors, constriction and obstruction, turn the Colorado River into a roller coaster ride.
It's very incompressible. So when you try to squeeze a volume of water, its size doesn't get smaller like many other materials. We have a fancy term for this. It's called bulk modulus, which is a function of how incompressible something is. Well, water is really hard. It might slip around a lot, but if you contain that volume, you can't compress it very much.
Even hard metals can be compressed. So why not water? H2O's dipole bond causes water to move with greater force through whatever's trying to contain it, like a narrow canyon, boulders in the riverbed, or a power plant. A dam the size of Hoover Dam is a triple threat. It tames floods, distributes irrigation water, and transforms water into power. But just how does a river become electrical current? It's all about harnessing water's non-stop downhill motion. The sheer height of the dam creates a huge difference in elevation between the upstream and downstream sides. As the water enters the intake towers, it falls about 700 feet.
The potential energy that's stored in a reservoir is proportional to the mass of the water that's stored in the reservoir. The potential energy is the mass times the acceleration of gravity times the height, the elevation at which the water is stored.
In other words, the more water you have, and the farther you can make it fall, the more energy you can convert.
So that potential energy then is converted to kinetic energy as that mass of water flows downhill.
The gravity-driven velocity of the water is increased by constriction as it's forced through narrower and narrower pipes.
Water is incompressible, but what happens is that same volume of water, in order to get into a smaller area, it has to move faster. And that same thing happens when they use it for hydroelectric power.
By the time the water enters one of the 17 turbine generators, it's moving at 60 miles per hour. The speed and pressure of the water are powerful enough to rotate these 114-ton shafts 180 times per minute. Each shaft spins a rotor, which is built of large electromagnets and surrounded by a coil of copper wire. The magnetic field between the magnets and the coil generates a massive electric current. In a split second, water is transformed into power. One current becomes another. Hydroelectric power provides about 24% of the world's electricity. But harnessing the power of water has its downside. Dams permanently flood vast ecosystems, and dammed reservoirs in hot, arid regions, like the lower Colorado Basin, also tend to evaporate quickly, which makes the water saltier when it's released downstream.
Also, when you store the water in the reservoir, it changes the temperature of the water. So when it's released downstream, it may not be appropriate for some of the native plants and animals which lived in the water previous to the building of the dam.
Dam or no dam, liquid water resumes its unstoppable course to the sea. Later, we'll see how frozen water flows. But next, without water, we would have never tamed the Wild West. The most diffuse state of water, steam, is perhaps its most muscular form. Converted into steam, water becomes mechanical energy, and lots of it. It takes a lot of energy to raise water's temperature, and even more to go from liquid water into a gas. For all the heat energy needed to bring water to the point of boiling, it takes 7 times that energy to then turn the boiling water into steam. But let's say you do apply huge amounts of energy. In this case, heat from wood and coal burned inside a pressurized boiler.
Well, that energy can be converted into something, including mechanical energy. So when water becomes a gas, and that gas is less dense than the liquid part, you can use that gas to create a force as it expands. So we can use steam to power motors.
Steam, the pure gas form of water, has its own peculiar properties. As it expands, it occupies 1,600 times the volume of liquid water, creating a great mechanical kick that can be harnessed to do work. That's the idea behind the machine that changed the world forever, the steam locomotive. On engine cars like these, the idea begins with water, lots of it.
We're standing on top of the tender tank. It's a great big U-shaped tank, and it holds about 2,000 gallons approximately.
The water is pumped from the tender tank to the boiler. A fuel source, wood or coal, is prepared to be burned.
We put a fire underneath it and boil water. And capture that expanding water, and the pressure works by pushing against something solid as it expands out. That's how we get the motion.
The steam bangs against the pistons, which then drive the wheels, moving the train along the track until it must stop for more water. It's easy to forget that in their heyday, these trains ran on water as much as they did wood or coal.
They would use 2,000 gallons of water in every 30 miles. So they had stops every 30 miles, more for the water than the wood.
Steam, for all its power, is invisible. The white vapor cloud we see coming from a locomotive is actually mist, tiny vapor droplets that form as the steam cools and condenses in the air. If you look at the spout of a steaming tea kettle, the spot where there appears to be nothing, that's steam. At the opposite extreme of water's life cycle, H2O takes on a much more visible form in ice. The solid form of water has everything to do with how water is distributed on Earth. And remember, it's less dense as a solid than as a liquid. So where does water go to slow down and kick back? Not surprisingly, Canada, where you'll find 20% of the world's fresh water, much of it frozen in the form of glaciers.
There remain a great number of glaciers in the Canadian West. There are more than 5,000 glaciers in the mountains that separate the Great Plains from the Pacific Ocean. But the largest ice mass in this region is the Columbia Icefield. It covers about 325 square kilometers and is in some places nearly 1,000 meters deep.
The Columbia Icefield is North America's hydrological apex, or triple continental divide, meaning that from this 12,000-foot-high summit, the melting ice will eventually feed into 3 different oceans, the Arctic, the Pacific, and the Atlantic. It's an incredibly rare phenomenon.
Glaciers are formed through cumulative snowfall. Snow builds up, it's compressed by its own weight and begins to form into ice. And as that accumulation continues beyond 30 meters, the ice will begin to change its shape and internal characteristics and begin to flow.
This water has been captured by the cold air, where it's been trapped for as much as tens of thousands of years. But despite its solid appearance, frozen water can still flow. Glaciers move. They're slowly moving rivers of ice that, much like liquid rivers, carve out valleys and prairies. Glaciers, with their slow but steady summer melt, are also key to the distribution of water on Earth. In fact, 75% of the world's fresh water is stored in glaciers. The Columbia Icefield is rare in another sense. The water here is pure enough to drink, right from the stream. Later, but how does sewage taste? Next, if you're looking for a tall drink of water, why not try the ocean? Water, water everywhere, and not a drop to drink. Perhaps, but desalination plants are turning that phrase on its head. We've seen water's relentless path from glaciers and snowmelt into mighty rivers. Eventually, all that fresh water finds its way to the ocean. So why are the oceans, which make up 97% of the world's water, too salty to drink?
The oceans have become salty because as rainwater and wind power and other forces erode the land, which is basically just a collection of rocks, and as those materials come apart, their chemical constituents run down into the ocean, and they reside there.
Many of these minerals are salts, including chloride, magnesium, potassium, and sodium. Over hundreds of millions of years, the oceans have gradually become saltier as the sun's heat vaporizes fresh water through evaporation. The water keeps cycling through, but the salt stays behind and accumulates. But human beings have found a way to make seawater drinkable and even tasty. It's called desalination. This is Tampa Bay Water's desalination plant, the largest plant of its kind in the United States.
You're not seeing the rains we used to get, so there's a lot of drought going on. So we're taking seawater from the bay here in Tampa, and we're taking all the salt out of it, and we're using it for potable drinking water for our region's needs.
Every day, the Tampa plant sucks up 44 million gallons of seawater from a nearby power plant, where it's used to cool the coal-burning boilers.
This is where the raw seawater is entering our plants, coming from the power plant. This is the first stage of our pre-treatment process. And what we do here is we add some chemicals, sodium hypochlorite and ferric chloride. The sodium hypochlorite is common bleach. We're trying to get the particles to settle and collect together, get heavy, and settle to the bottom.
After screens filter out shells and other larger debris, the water passes through these sand filters. The grains of sand filter out some particulates and some of the salt. The water passes through another set of filters, which remove even smaller particles. But how do you remove all of that dissolved salt? The Tampa plant uses a high-powered version of reverse osmosis. The salty water is blasted with great pressure, 1,000 pounds per square inch, through rolls composed of thin membranes, each one outfitted with pores that are 1/100,000th the diameter of a human hair.
That's how small it is to capture these salt particles. And the pure drinking water eventually gets to the center, and that's the water we're going to drink. The salty solution, the brine, is going to spiral its way out.
The reverse osmosis process is so effective that plant engineers have to remineralize the water after it's passed through. Why put minerals back in the water? Well, it's actually dangerous for humans to drink large amounts of 100% H2O, since the water, stripped of minerals, will begin leaching out the beneficial minerals in our own bodies. In less than an hour, the plant transforms salty wastewater into pure drinking water. This facility supplies 10% of the Tampa region's municipal water. But no water, not even treated sewage water, is beneath salvaging. At the other end of the continent, another water-challenged coast is digging deep for water solutions. In Orange County, California, an advanced purification facility takes a different form of non-potable water, treated sewage from a nearby sanitation district, and makes it fit for drinking.
On a daily basis, we receive about 104 million gallons of secondary effluent from the Orange County Sanitation District. Out of that, we produce 70 million gallons of ultra-purified water. It's a tremendous amount of water. It actually will produce enough water for 500,000 people in northern and central Orange County.
The process is a lot like desalination. A rigorous microfiltration process removes the larger waste sediments. Then, the nation's largest reverse osmosis system removes smaller pollutants, in this case, down to the size of a virus.
The water, after it goes through the reverse osmosis, is very, very pure. However, there are some small, low-weight molecular organic compounds that can get through the reverse osmosis. And that's why we've added the UV light with hydrogen peroxide.
In this final step, individual photons of ultraviolet light combined with hydrogen peroxide neutralize any remaining undesirable chemical compounds. The former sewage effluent is now purer than most tap water or bottled water.
We actually have to remove a lot of compounds down to the parts per trillion level. Not million, not billion, but trillion. I absolutely drink the water from this plant. In fact, we have a sample sink in the back, and I'd be glad to take a drink of the water before we're done with our interview.
A man of his word. Skeptics of this so-called toilet-to-tap technology needn't worry. Pure as it is, this water doesn't go directly into the municipal water supply. Instead, just to be sure, it gets yet another round of filtering. Half of the water is pumped 13 miles to this basin in Anaheim, where it then percolates underground back into the local aquifer.
An aquifer is a layer of sand or gravel or other permeable material that can transmit water effectively, and in particular, it can transmit water to a well.
As the water percolates through the sand and gravel layers, it gets another natural form of filtering before it joins any municipal water supplies. The other half of the treated water is pumped into an underground sea barrier that protects the local aquifer against encroaching saltwater.
So if the water level in the groundwater basin is below sea level, there can be a gradient for water to flow from the ocean through the aquifers into the groundwater basin. So we inject water along the coast to make a hydraulic barrier so that that hydraulic barrier prevents seawater from flowing in the aquifers into the basin.
In regions like Southern California, which depend on distant snowmelt for most of their water, any local water is crucial. If this water recycling plant didn't exist, every day 104 million gallons of treated sewage would simply be pumped into the ocean. Instead, the newly purified water stays within the local freshwater system. In dry regions, every drop counts. So that next glass of water might be treated sea or sewage water. And it just might be cleaner than expensive bottled water. Next, if you want to be a rainmaker, all you have to do is plant the seeds. Look up into the atmosphere, and what you're really seeing are liquid skies. If only we could coax some of that water vapor down to Earth in arid regions of the globe. But wait, we can by putting tiny seeds into the clouds. Some scientists estimate that the amount of water floating in the Earth's atmosphere is 6 times greater than that flowing in all the world's rivers. But most of that airborne water is in the form of vapor. When that vapor rises high into the atmosphere, it cools and condenses into tiny droplets of water or ice, each about 0.02 of a millimeter across. These droplets gather into what we see as clouds. But how do clouds become rain? It's not so easy. In one of the more peculiar of water's many peculiar properties, the droplets, not unlike a pearl, must form around a tiny imperfection, a bit of dust or debris known as a cloud condensation nucleus, or a cloud seed, in order to grow heavy enough to fall from the sky. This tiny trick of nature is not happening often enough in some parts of the world, like the Texas South Plains region, which has experienced frequent and severe droughts in recent years. Making things worse, the Ogallala Aquifer, which provides irrigation water to parts of 8 western states, including Texas, is being sucked dry faster than rainfall can replenish it. And so, Gary Walker and his company, SOAR, perform a high-tech version of the rain dance, an attempt to wring precious water from clouds that just don't want to rain.
In this area, the 2 main sources of water are the Ogallala Aquifer, which is an underground aquifer, and rainwater. In possibly the next 10 to 20 years, there would not be the capability to pump enough water out of the aquifer for irrigation purposes.
SOAR's proposed solution is known as cloud seeding. Gary's going to fly his twin-engine Piper into a cloud, armed with rocket flares of silver iodide. The silver iodide particles will act as cloud condensation nuclei.
The particles are extremely tiny. There's about 13 trillion particles of silver iodide in that 20-gram flare right there. We're now ready to go on a seeding mission.
First, the plane must find a suitable cloud at an altitude of 18,000 feet, where the supercooled water droplets might be ready to form raindrops. Meteorologist James Dryden guides Gary Walker's plane into position.
All right, Seed One, basically you're approaching the New Mexico state border, so we need to go ahead and turn around. Let's go ahead and get you on the south side of the storm from your current location. Track would be 203 at 9 nautical miles.
Charlie, we're going to penetrate at about 11,000.
Gary fires the silver iodide flares into the cloud.
There goes a flare. Good updrafts, 1,000 feet a minute. There's another flare.
The updrafts carry the silver iodide particles into the upper regions of the cloud. If the conditions are just right, we can expect to see raindrops falling in less than 45 minutes. But today, there's simply not enough water vapor to form raindrops. Another dry day in Texas. But the cloud seeding program has made a difference.
Our analysis has shown about 10 to 12% additional rainfall out of seeded clouds versus non-seeded clouds, and that would equate to about another inch to an inch point 2 of rainfall during the growing season. So if we create an inch of water over our seeding area in the summertime, it's thousands and thousands of acre feet of water.
In an era of accelerated climate change, reliable water supplies will be harder to come by here on the Texas plains and back at the Columbia ice field, where global warming is threatening the ancient stores of glacial water.
Glaciers are water in the bank. That is water held from earlier historical times and carried into our time, and when it melts, it contributes to the flow regimes of existing river systems.
If glaciers are water in the bank, there's a run on that bank in the form of accelerated melt. Like many other glaciers, the 4-mile-long Athabasca Glacier is receding dramatically and losing vertical mass with year after warm year. The rapid melting will mean more flooding, but in a cruel paradox, less opportunity to harness the water we've gotten used to having.
What will happen is that we will have less water than we have designed our systems for, and therefore we'll be facing water scarcity in many parts of the country that never faced water scarcity in late summer before.
21st century water scarcity is yet another challenge for human beings as we struggle mightily with the fluid of life, bringing it to places that would otherwise never see it, transforming it into power, machinery, and abundance, reclaiming it from the oceans, sewers, and even rearranging the weather to make more of it fall to earth. But water, in its utter uniqueness, stubbornly resists change. It will always seek its downhill path, from the mountains to the sea. It will continue to dissolve whatever it picks up along the way. It will refuse to be compressed, and it will not create any more of itself, no matter what we do.
What happens to this river happens to us. It may not happen immediately, but it will happen eventually. All of those actions have repercussions on us as humans and as a civilization. I think it would behoove us to be a little more mindful of what we do to our rivers. Keeping them a little more pristine, a little more wild, a little cleaner would definitely do us good as a society.
Pouco de frio no caminho.